In this video, we will introduce a phenomenon called quantum entanglement and discuss concepts associated with it. What is quantum entanglement? It is that two quantum particles can be coupled in such a way that their properties are no longer independent of one another, no matter how far apart they are. We say that the particles are entangled. Imagine you have a pair of gloves that are distinguishable. You put them separately into identical bags. You mix them up until you don't know which one is which. Choose a bag and send it somewhere far, far away, and keep the remaining one. As soon as you open the bag and check that you have the right glove, it is instantaneously determined that the abandoned bag contains the left glove. This analogy, however, is somewhat erroneous. In classical interpretation, the nature of the gloves is predetermined. If the left glove has been put in the bag, it will always stay the same. However, in quantum mechanics, the two states, left and right, coexist until an observation is made. This coexistence of two or more states is called superposition. But after a measurement is made, we can only see one state. This is because the wave function describing the system collapses when an observation is made. Essentially, we have two bags each containing both left and right gloves. But when one is observed and fixed as one state, the other bag automatically and instantaneously contains the opposing state.
This is where Einstein got triggered. According to his theory of relativity, nothing can be faster than speed of light. This includes the communication between the gloves and their states are to be determined. How can this process be instant when they are infinitely apart? It is also worth knowing that the entanglement violates the principle of locality, which is one of the essences of classical mechanics and Einstein's theory of relativity. No wonder he was so eager to disprove quantum mechanics. He therefore questions the validity of wave functions in describing the physical reality. Einstein and two other scientists, Podolsky and Rosen, presented their paper. In this paper, they first suggest the criterion for physical reality. Then they first assume that the wave function does contain a complete description of physical reality of the system for given states. But using proof by contradiction, skipping the full derivation, EPR conclude that the quantum mechanical description of physical reality given by wave functions is not complete. But experimentally, entangled particles have always shown correlation, regardless of how far apart they are. If one particle has spin up, the other particle always has spin down. There are no single exceptions of up, up, or down, down. Einstein proposed that there must be a hidden variable to account for this spooky action at a distance.
In 1964, J.S. Bell published his theorem. It says the number of objects which have parameter A but not parameter B plus the number of objects which have parameter B but not parameter C is greater than or equal to the number of objects which have parameter A but not parameter C. What? And this inequality is shown in the Venn diagram. And it seems intuitively obvious that if you add up the first two areas, the sum is going to contain the third area. So the sum of the two is greater than the third area. This idea can be applied to the measurement of electron spin. We can substitute A, B, and C with other quantities, such as the angular orientation of an electron and its spin. Then we can set up experiments to test the new inequality. These are the assumptions behind this methodology. Logic is valid, electrons have predetermined spin, and no information can travel faster than the speed of light, which means the system follows locality. If we think of information about electron spin as a hidden variable, then the assumptions become: logic is valid, hidden variables exist, and hidden variables are local. The result obtained after actually doing this experiment is that this inequality is violated. Electrons do not have predetermined spins. Their properties are described by wave functions, and until a measurement forces the wave function to collapse, multiple possibilities exist at the same time. The violation of Bell's inequality means at least one of the three assumptions has to be wrong. Whoops, Einstein's hidden variable idea does not seem to be working. The contradiction of Bell's inequality implies that no physical theory of local hidden variables can ever reproduce all of the predictions of quantum mechanics. This means that entanglement cannot be explained in a classical manner, and to correctly describe it, quantum mechanics is needed.
As one last remark, we want to comment on how we describe quantum entanglement as a communication. It is actually inaccurate to describe like so, because communication means that the user wants to deliver his or her desired message. Let's say that when the recipient at the nexus opens his box, he understands spin up as a yes and down as a no. The person on Earth will observe the box and get either spin up or down by probability. Naturally, the recipient at the nexus will observe just the exact opposite result. Even if the person on Earth wants to say yes, it may be delivered as a no due to the probabilistic nature of quantum mechanics. In other words, the term communication is misleading, as the sender does not have control over their intended message. Thank you for watching.